Lesson 9-6 is the lesson that we've been over the last several days and I guess weeks been working our way towards. It's basically where all the work you did with exponential functions and learning about logarithms and solving equations pays off. You can now deal with real life, real world situations and make sense of them because of the tools you have in your toolkit. So let's get after it and see what there is to figure out here. One way to kind of think about this lesson, but also solving equations of this sort in general, is that they fall into two bins. Either you're talking about some sort of exponential decay or you're talking about some sort of exponential growth. And once you're in those two bins, which are, it's pretty easy to figure out which bin you're in, then there's two more bins. The decay that you're talking about can be periodic, meaning it happens over regular intervals, or it can be continuous, meaning it happens without interruption. The same is true for exponential growth. You can have periodic varieties or you can have continuous varieties. This is a subtraction sign, by the way. Notice that the equations that go along with them are pretty similar. Some of the obvious differences are that for decay, you have 100% of what you begin with and you're subtracting some amount, whereas with growth, you begin with 100%, you add on some value. When it comes to the continuous equations, they are identical with the exception of the sign of k. K is just some constant, basically describing the rate at which something is either decaying or growing. Here, because this negative or this k is negative, you're essentially taking the inverse of e, which is a fraction less than 1. So that's going to cause decay. Here, that k value is positive, and so whatever this base is, it's going to be greater than 1. You're going to have growth. One last thing to kind of note is that at the end of the day, these are models in math. Remember that math models are never intended to be perfect. We will have issues with them as far as them being the best models. Sometimes we'll feel like they're not the best models, and that's okay. It's much better to have a model than to not have any sense at all about what's going on in a certain situation. So we'll start off with a pretty kind of uh, ordinary problem. It's about car depreciation. I took this right from the book, and it basically reminds you, you may not know this, that most of the assets we actually buy, most of the things we buy, tend to depreciate or lose value over time. Cars are a prime example of that. And in this case, when the car is brand new, it's worth $22,000. A year later, it's worth about $18,500. And then, as you can see, as the years go by, it has less and less of its value remaining. What can initially be puzzling is it says that the value of the car decreases by 16% each year. So you might expect that these differences would be the same, but they're not because the first year, 16% of the value disappears. And then the next year, 16% of a new amount disappears. So you would not expect common differences here. There's going to be a common ratio. So, just to kind of ground this a little bit more in reality, if you do an internet search on car depreciation, there are known values for different cars. If you buy, I don't know, an Audi, for instance, a relatively expensive luxury car, on average, they will depreciate by about 40% over the course of 3 years. So you're going to lose 40% of your value over the course of a number of years. BMWs lose about 35% of their value over the course of time. Now, those are both considered luxury vehicles. For something like a Chevrolet, we're talking about 55% of the value of the car is lost over the course of 3 years. And as you kind of scroll down this list, different cars have dramatically different depreciation rates. Um, if you click further into these categories, you can then see specific makes and models. So Honda Accords, for instance, depreciate about 35% in the first 3 years when new. So, to even kind of open up the conversation a little bit further, think about what's been happening over the course of the last few decades in our economy. The cost of things that are essential, things like healthcare, home ownership, the cost of an education, cost of food. Those are essentials, things that you really kind of need to survive. The costs for those things have skyrocketed. They've really kind of reached unprecedented highs. And then on the other hand, the cost of commodities like TVs, gadgets, computers, electronics, appliances, those have have dropped considerably. So much so that people have so much stuff in their lives that one of the biggest industries in the US right now is self-storage. Self-storage companies actually are more profitable than Hollywood now. They make more money than all Hollywood films combined in a particular year. So I guess what I'm trying to say is that this idea of things losing value and the idea of things increasing in value is all over the place. One last thing to mention is that it's not all bad news if a car loses value over the course of time. In the city of Boston, for instance, we pay something called an excise tax. So every year, the city of Boston forces you to pay tax for owning a car in the city. And the way they compute that tax is they charge you $25 per every $1,000 of value that your car has. So in a weird way, the less your car is worth, the less excise tax you pay. So a lot of people choose not to buy cars new. They choose to buy only used cars for many reasons. One of them is so that they can pay a lower excise tax. Finally, with respect to that problem, I just wanted you to see that one way to kind of take stock of what that car is worth is to use this kind of periodic depreciation formula, this A times 1 minus R to the T power. The initial value of the car in our example was $22,000. It loses 16% of its value on a yearly basis, meaning that what's really happening is you keep multiplying the initial value of the car, that $22,000, by about 84% for however many years you own the car, or for however many years have passed since the car was new. So this example illustrates what it means to have some periodic decay. The value of something is decreasing over the course of time at regular intervals. Let's have a look at a second problem here, a little bit more grounded in the world of science here. And what I want to say about this problem right off the bat is that even though we're using this same kind of periodic decay model, it's probably actually much better modeled by using the continuous decay. So you might say, well, why are you using this model at all? Because it's a model at the end of the day. There's no expectation of perfection. It will still give us a sense as to what's going on in this situation. Um, so we're talking about metabolizing a drug here. And that drug happens to be caffeine. It's probably the most widely used drug uh, on the planet. But this problem could just as easily have been about metabolizing something like alcohol or aspirin or any number of drugs. So in this case, the situation is that a particular cup of coffee has about 130 milligrams of caffeine. For this person, and this depends on the person, but this person eliminates caffeine from their body at a rate of about 11% per hour. How long will it take for half of this caffeine to be eliminated? It's also interesting to note that according to this model, you never actually completely eliminate caffeine from your body because there will always be some vestige of it, some trace amount of it left in your body. And there's a follow-up question, which is how long will it take for 90% of the caffeine, most of the caffeine, to be eliminated? So you've got a couple of facts and figures here. You've got the initial amount of 130. That's probably going to replace this A value. You've got the fact that 11% of the coffee, or excuse me, caffeine is disappearing per hour. So we're going to replace that rate with 11% or 0.11. So let's see what that looks like mathematically. Take a look at the work that goes along with it. So here's the first kind of phase here where I've used the formula and I'm interested in how long it takes for half of the caffeine to be eliminated. So half, the outcome that I'm looking for, half of 130 is 65 milligrams of caffeine. The starting amount is 130, and I'm subtracting 11% from that 100%. And then this is really a key moment, kind of a momentous occasion, because once you get that 0.89, and on this side you've got 65 divided by 130 as a half, you cannot solve this equation algebraically if you don't know about logarithms. And so, it's really gratifying to have done all that work so that now you can access. You want to know how long does it take, and that variable is up in the exponent there. So you find the common logarithm of both sides, or any logarithm you want. I've chosen to use the common logarithm here. And what it does is it brings that exponent down and makes it into a factor because you have the power raised to a power. So once I have that t Among my variable here, or among my linear factors here, I can just divide both sides by the log of 0.89, and you find that it takes about 6 hours to eliminate half of that caffeine from that cup of coffee. The follow-up question wanted to know how long does it take to eliminate 90% of that caffeine. So I went and found 90% of 130 milligrams, and I ended up with 117 milligrams. So the target that I'm looking for is if 90% is eliminated, then I'm just left with 13 milligrams. So once more, I've made use of the same equation, except my target is no longer 65, it's now 13. Algebraically, I follow the same exact steps, and you realize that it can almost take a full day to eliminate the majority of the coffee there. Of course, you can increase the rate at which you're metabolizing caffeine by drinking water as well to wash it away essentially. But I hope that that was a good kind of example of what it means to use that periodic model to figure out what's going on. Let's take a look at one more problem in this video, and then we'll pause and pick it up in the next video. So this problem is about also exponential decay, but of the continuous variety. You notice that I'm using the different equation here, and probably one of the most common examples that is used here for uh, continuous decay is radioactive decay. And the premise is that most substances or many substances have a form, an isotope, that is not stable. So carbon is basically the building block of all life forms. Anything that is alive, insects, animals, us, has carbon in it, plants. And most of that carbon is found in the form of carbon 12 or 13, but some small trace amount is carbon 14, and it's unstable and it decays at a known rate. So as that carbon 14 decays, uh, what's happening is we can measure that rate of decay and figure out how old something is. So here's the problem. You've got the half-life of a substance is the time it takes for half of the atoms of the substance to disintegrate. All life on Earth contains carbon-14, and the half-life of carbon-14 is 5,760 years. That doesn't mean it all disappears in that amount of time. Half of it disappears in that amount of time. And then whatever's left takes another 5,760 years to decay, and so on and so forth, until there's such little carbon-14 left in the sample that you can't even detect it. We don't have the instruments to detect it. So two questions. One is, what's the equation of decay for carbon-14 in particular? And two, you've got a paleontologist who has found the bones of a woolly mammoth, and they estimate that there's only about 3% as much carbon-14 as when that mammoth was alive. Can we figure out how long ago that mammoth passed away? And in doing so, figure out how old the bones are. So you've got quite a bit of information here. Let's see how I resolved it. Just adjust the camera here so we can see the story in its entirety. So here's that initial equation, this kind of continuous decay equation. And I've done two things, well, maybe three that are significant. One is the outcome is a half. Right? We're looking for the half-life. So I've replaced that y value with a half. The initial amount is just 1 here. You're starting with 100% of a sample when the creature was alive. And then I've taken that time, that t-value, and replaced it with 5,760. The natural base, is a known value, so there's only one unknown in this whole equation, and that's the letter K. I'm looking for the constant for carbon-14. What is noteworthy here is that when it comes to solving this equation here, the one that I'm kind of hovering around, you need to be able to use logarithms yet again in order to solve for k. So I haven't taken the common logarithm this time. I've taken the natural logarithm, or ln, of both sides. And in doing so, again, it allows this exponent to become accessible. Log base e of e cancels these out, leaving you with just negative 5760k. You end up with this constant here, which is specific to carbon-14. So if I want an equation for carbon-14, it's this y equals ae to the negative this constant t-value. So now I have the tool in hand that I need to figure out how old these mammoth bones are. Uh, the sample contained only 3% of what it started with, and what it started with was 100%, 1, which I'm going to no longer show afterward, but that's a 1, and that's an E. Here's my constant that I'm actually fitting in, and what I'm looking to solve for is time. How old are the mammoth bones? So again, same algebraic journey. If you've been solving these equations, this is pretty familiar to you. And we find that those mammoth bones are about 29,000 years old. They lived in the last ice age, so this is a reasonable value to end up with here. In the next video, I'm going to go from talking about decay to talking about growth. So I hope to see you there.